Section 2.2. An element's properties depend on atomic structure. Each element is made up of unique atoms. Remember, atoms are the smallest unit of matter that's still considered that element. They're made of subatomic particles. Protons and neutrons make up the nucleus of the atom. A proton weighs 1.7 times 10 to the negative 24 grams per particle, and a neutron weighs roughly the same. So together, they make up the atomic mass. So number of protons, number of neutrons equals atomic mass. We talk about the atomic number. We can find that on our periodic table. That gives us the identity of the element or the atom. The identity, that atomic number, is kind of like the social security number of an atom. It never changes. The electrons are found in the shell. You might also hear it called a cloud or an energy level. Sometimes you'll hear it called a valence, and that just refers to the outermost shell. An electron is very tiny. They do not contribute to the atomic mass at all. They weigh 1/2000th of what a proton weighs. So they're very, very tiny. And the fun thing about that is we really don't even know exactly where they're found. We came up with this electron cloud theory to explain this is probably where you're going to find electrons at. An isotope is an atom that has different numbers of neutrons. In an element with the same number of protons but different number of neutrons, we get radioactive isotopes that can decay due to nuclear instability. Decay is a constant thing, and we can actually use that to our advantage by using the half-life of things to determine a biological age. So in carbon-14 dating. Electrons are what determine the reactivity of an atom, or how it's going to interact with other atoms. And that's what also gives it its charge. A neutral atom has no net charge. It has the same number of protons, neutrons, and electrons. It's a happy atom. So for example, lithium has an equal number of protons as it does electrons. Remember, neutrons have no charge, so they don't contribute to the reactivity. However, if we have a lithium ion that's missing an electron, it now has a +1 charge. The differences in those are called ions. A cation is when an atom is positive. It has a positive charge because it has lost an electron. Anions have negative charges because they have somehow gained another electron. And again, that orbital is just the area where the electrons are most likely to be found. Each orbital can't hold more than 2 electrons. So when we're looking at atomic structure, we have a nucleus that has a given number of protons and neutrons. Then we have this first shell or cloud, and it can only hold 2 electrons. That's how small it is. The next shell can hold up to 8, and we call that the octet rule. Now that's not saying that all atoms are going to have 8, but it can hold up to 8. Make those evenly spread. So those electrons determine the chemical behaviors of atoms because that's where those interactions or chemical bonds occur. A redox reaction is when there's been a loss of an electron and somebody gains it. So Leo says grr, Leo the lion says grr. Oxidation is when an atom loses an electron. Reduction is when it gains an electron. And that energy level is based on the electron distance from the nucleus. That first shell that's the closest one to the nucleus is going to be a very, very strong pull, whereas the ones that are farther away, not as strongly attracted to the nucleus. That brings us to the periodic table. It was organized by Dmitry Mendeleev. He's considered the father of the periodic table. The story goes that he had all of the elements that were known at the time written on note cards, and he had tried to organize them based off of different properties. And he fell asleep with the cards under his pillow. When he woke up, he'd had a dream that he should organize them to look like this. And so what you're looking at, it looks kind of silly, but it makes sense. We have different groups, so like group 1, group 2, and they are based off of the chemical properties. And those chemical properties repeat with every 8 elements. So we have 1, 2, back here to 3, 4, 5, 6, 7, 8, 9, 10. And so 2 and 10 are going to share chemical properties. The valence electron refers to the electron that's in the outermost shell. So it's not talking about the ones that are on the inside. And then the octet rule, all the atoms want to be happy with a full outer shell, meaning they hold 8, except for the first circle. It only holds 2. This first group here is the alkali metals. The second one is alkaline earth metals. Both of these are very reactive metals, this one more so. This group has 1 electron in its outermost shell, so it's very desperate to get rid of that so that it can have a happy full outer shell. Then we have our heavy metals down here. These guys don't really follow the rules. They're kind of the rebels of the chemical world. The metalloids border, it's these green guys, they border this bold dark line. And that dark line is what divides our metals on the periodic table from our non-metals on the periodic table. The metalloids are kind of like metal, but not really. The non-metals, like carbon, nitrogen, and oxygen, you may notice most of them are gases. Our halogens make up group 7. Those halogens are very, very reactive, and they really like to react with the alkali metals. Those types of bonds are called ionic because we have a metal and a non-metal. Now these noble gases here in blue on the end, their outer shell is full, so they are considered inert or non-reactive. They don't want to change anything about their atomic structure. A chemical bond is just how atoms connect to each other in a molecule, and then the molecules combine to form compounds. Those ionic bonds are the ones that form between oppositely charged atoms, or a metal and a nonmetal, so somebody from the left with somebody from the right. Covalently bonded molecules are going to share electrons, and this is where you have nonmetals with nonmetals. They have no net charge, and those covalent molecules are going to form our sugars and a lot of our basic carbon-based molecules that we're studying. So a single bond is when one electron is shared from one atom to another. It forms a pair. When we draw it, we use a single line between the 2 atoms. If it's a double bond, there's 2 lines. That means there are 2 electrons being shared. A triple bond, which is the strongest we're going to see, is 3 lines. That means that 3 electrons are being shared. And so if we were to draw this out, we can see we've got our carbon atom here with 6 protons, 6 neutrons in the nucleus, our first 2 electrons, and then the remaining 4, which means we have 4 holes to fill in that outer shell. Now, why can't a carbon have a quadruple bond? Because if carbon could bond to carbon, why would it ever leave and find anybody else to bond with? If it could bond with itself, it wouldn't have the need to form other compounds, and so life probably wouldn't exist. So a structural formula is one that shows the actual elements in the compound, and it shows their bonds between them. That's going to come into play in Chapter 4 when we start talking about those molecules. The single lines come off to those hydrogens. You can see we have a double bond here between this. We won't get into the naming of the hydrocarbons, even though that's one of my favorite things to do. Molecular formulas just give us the elements in a compound. So this element right here and this element right here are represented in the same way by this molecular formula, C4H8. A chemical reaction is made up of reactants and products. Reactants and reactants are what's going into the chemical reaction, and then it's going to yield or produce or make or form whatever the product may be. So the product is what's being produced, what's coming out. Dynamic equilibrium is the state that most of our biological reactions are trying to reach, where you have equal numbers of reactants and products and they're back and forth, back and forth. Biogeochemical cycles and biochemical cycles are in this state of dynamic equilibrium. That's how we maintain homeostasis. And the factors that influence reactions, temperature is one of them. We can increase the rate of a reaction by heating it up. Think about dissolving sugar in a pan of water. If you add heat to it, it's going to dissolve faster. So molecules can actually be destroyed when they get too high. So if we get our enzymes to a temperature that's too high for them to maintain their structure, they actually fall apart, which is one of the reasons why when you have a fever, you're no longer hungry, because your digestive enzymes have gotten too hot, lost their shape, and now they don't work. So that's the cause of the I'm not hungry when I have the flu or a fever. A catalyst is anything that increases the reaction rate. It lowers the activation energy, and the example that we use from our body is an enzyme. Remember, enzymes are proteins, and those catalysts are allowing chemical reactions to happen that would take a very long time. But because we don't have a long time, such as our digestive tract, those enzymes are present to help that digestive process along.